Hello everyone and welcome back to another video. Today I shall on resistor number Iwaki 20CS2036. I'm going to explain to you experiment number 5 of OS labs. Today we'll be doing classic synchronization problems. These include 3 problems, which is a producer-consumer problem, a reader-writer problem, and a dining philosopher. All of these use lock concept and multi-threading. So the first we are going to be looking at is producer-consumer problem. In this we'll be importing threading and time. Threading will be importing for multi-threading, and time will be importing for setting the lock, mutex locks and semaphores. We have shared memory variables, that is capacity of 10, so the buffer size is 10. We will be creating for -1 in the range of capacity, that is we will be creating a list of size 10 with -1 filled in all of them, and later we will be changing that to 1 when the producer is adding in items, and the same with consumer. The consumer will be consuming the items. So we have an in index and an out index, that is in index is incremented every time the producer consumes, and the out index is increased every time the consumer consumes. Then we have mutex, which is threading dot semaphore, that is a lock, and then we have empty, which is also another semaphore of size capacity, is a binary semaphore, and this is a counter semaphore. The same with full, which is a counter semaphore of size 0 initially, and every time the producer produces we will be incrementing this. So let's see how it's done. So this is the producer class, and when we run this, at the time the items produced initially will be 0, counter will be 0, and while items produced is less than 20, T will be acquired, empty semaphore. Mutex semaphore also is acquired. The counter is incremented by 1, that is item has been created and that is at the counter, and dot in index will be getting the value of the counter, and then in index is equal to in index plus 1 by capacity, that is in index will be incremented by 1 and it will be modded by capacity, so that if it goes beyond the size of the capacity, again inside the limit of the capacity. So that's why the index should be within the list size, that's why we use this mod of capacity. And then after that we print that the producer has produced the so and so nth item, and then we release the mutex lock, and the full also we release, that is we decrement full by 1, and empty is acquired, so empty gets incremented by 1. And then here we put it to sleep for 0.5 seconds, and then items produced also is incremented by 1. Then when it comes to consumer, here the items consumed initially will be equal to 0, but while items consumed is less than 20, full will be incremented by 1 because we are going to be consuming 1 item. Mutex will be acquired, so that the producer can't produce when the consumer is consuming, so that the shared memory cannot be used by both together. So the mutex is acquired here, and after it is acquired, item is equal to buffer dot out index. So the out index initially it will be 0, so from there the out index it will be consuming, and then we will be incrementing the out index by 1 and modding that by capacity. So that will give us the next index, so that next time when it runs, that time it will look for the next out index. And then we print that the consumer has consumed the so and so item, and then mutex dot release and empty dot release. So empty will be incremented again by 1 and mutex will be released. Then it will sleep for 1.5 seconds and time consumed is incremented by 1. And so after we make both these functions, the run functions will run when we create the threads over here, that is producer is equal to producer function and consumer is consumer function, and then we start the threads, and then finally we said that we are waiting for the threads to complete, and producer dot join and consumer dot join, that is we join both the threads into running. And after that, as you can see here, the producer produced 1 item, consumer consumed 1 item, producer produced items, and then consumer consumed a few items, and so on. It keeps going on till 20 items because we have set the limit as 20. And then we have reader writer problem. In this we import threading as a thread, and here we have a read C variable, and in this we have also a random, we will be importing random library, and just for getting random output and randomly running the threads for that. And X is the shared thread, so we will be setting X initially as this is shared stuff, and after that we will be setting a read count to be 0, like how many readers are reading currently, that is reading of currently is equal to 0. And then we have a mutex is equal to thread dot lock, and read write mutex is again a thread dot lock, so we need both these. Mutex is for changing the reader count, and read write mutex is for either reading or for writing. So here the reader function is that we have a global C and X, then we have mutex dot acquire. So the mutex lock will be acquired as mutex semaphore, and after that we will be incrementing the reader by 1 since now we are reading. And then if the reader is incremented by 1, then in that case we will be acquiring the read write mutex. Once we acquire that, if the reader count has incremented, we will be releasing the mutex count, and after that we will be saying reader is reading and shared data is X. And once after that we will be acquiring the mutex again so that we can decrease the reader by 1 because our reader has finished reading. And after that we will be decrement the reader count by 1, and then we will be checking if the reader count is equal to 0, that is no reader is reading, then we can release the read write mutex. And once after that is released, then since we are no longer reading the reader count, we will be releasing the mutex release, that is the mutex lock for read count also will be released. Then the same for writer. In writer we don't need to change the read count because multiple readers may read, but there can only be one writer writing at a time. So we have a read write mutex dot acquire over here, so we acquire the read write mutex lock, and after that writer will be writing whatever it wants to write, and after that the read write mutex will be released, and then it prints to the next line. So here we have used the random function for running this main function. In this main function, in the range of 0 to 10, we will be printing that if we will be taking a random number using this random integer between 0 and 100, so it will give a random integer between 0 and 100. Here we have just put a probability function that if it is greater than 50, in that case we will be running the reader, else we will be running the writer. So let's run this program and see. So as you can see, the writer started writing, and then the reader read in between, and then again the writer is writing, and this is shared. And then let's move on to the Dyna Philosophers problem. So import threading and import random and import time. So we import 3 libraries, and then we have a class of philosophers. In this, every time we initialize a philosopher, we'll be giving it its own thread, and on that thread this philosopher will run. The philosopher will have an index, and it will have an index of a left fork and a right fork. So these are kind of like, you can say kind of like locks, but this will be only initialized to the left fork and the right fork every time the philosopher is eating. So here then we have the run function. So when we start the thread, the time the philosopher will be thinking, and but in reality we only put the philosopher's thread to sleep, and when the philosopher is hungry we call the dine function. And here we will be running this, and we will be, both the forks are actually semaphores. So if both the forks of a philosopher are free, only then he can eat. So fork 1 and fork 2 are self dot fork on the left and self dot fork on the right. While self dot running, we acquire fork 1, and when we acquire fork 1, we check for the locked condition. Locked is equal to fork 2 dot acquire of false, that is we will be checking if fork 2 can be acquired. If locked, that is if the right fork which we picked up is available but the left fork is not available, then in that case the previous fork also be released, so that if there are other philosophers that need the fork, they can use it. And after that we say that philosopher, whichever number the philosopher's index is, that philosopher is going to swap his forks. So whichever fork was under use, which was occupied by some other philosopher, we will switch that fork to our primary fork, and we will be waiting for it to acquire. So whenever we can acquire that, then hopefully the other fork will be free, and that way this philosopher can eat. And else we will be returning self-dot dining. Self-dot dining will be returning that the philosopher starts eating, and then in 30 milliseconds the philosopher eats. The philosopher finishes eating and leaves to think. And after that, here we have the main function. In this we will be having forks is equal to threading dot semaphores for n in the range of 5. So it will be basically all the forks that we will be creating are 5 semaphores for 5 philosophers. And after that the philosophers will be creating, that is philosopher comma I of fork of I by percentage 5, and then fork of I plus 1 percentage 5. So essentially each philosopher will be getting the current fork and the next fork, and that will be done for range of 5. And after that, when the philosopher is running true, then in that case for the philosophers we will be starting all the philosopher threads, and then we will be putting the thread to sleep for 100 seconds, and philosopher running is equal to false. Now we can say that the philosophers have finished eating, that is after the threads have all run. All the philosophers have completed eating. Once they have all started eating, finished eating, and have thought and finished thinking, and again eaten and all, after that finally we can tell that now we are finishing, and then finally we run the main function. So when we run this, as you can see, philosopher 1 gets hungry, then philosopher 2 finishes eating and starts to think, philosopher 3 is eating, philosopher 4 is hungry, and so on. Philosopher 0 swaps forks. Maybe he didn't get the second fork, so he now is waiting for the second fork, and then philosopher 0 starts eating, because right now philosopher 1 finishes eating and leaves to think. So then the second fork of philosopher 0 will be released, and that time then philosopher 0 can eat and start eating, and so on. It is done quite a lot, and then finally the philosophers, they say that philosopher, we are done eating, so we are finishing. So that is what they say, and they leave. So this is all for experiment number 5. Hope you like this video. If you did, do give it a like, and do subscribe to my channel for more such interesting videos. Hope to see you guys in the next video.